everyone, thank you so much for clicking onto this video. Today we're going to be looking at combined techniques. So our learning objective is to look at the deduction of the structures of organic compounds from different analytical data, including elemental analysis, mass spectra, infrared spectra, and NMR spectra. Now we're going to look at combining all the techniques that we've learned. So we can use a combination of techniques to identify organic compounds and determine their structures, including mass spectrometry, which allows us to determine the accurate relative molecular mass of a compound, and also the fragmentation patterns, which can suggest possible groups present. We can also use infrared spectroscopy, which allows us to identify particular functional groups which are present in an organic compound, and then also NMR spectroscopy, so carbon-13 NMR, which allows us to identify the number of different environments for carbon atoms in a compound. And then we also have hydrogen-1 or proton NMR, which allows us to identify groups of hydrogen atoms in a compound. And another thing with the proton NMR is that we also get splitting patterns. And these allow us to identify the number of hydrogen atoms on an adjacent carbon atom. So in this example, a compound is made of 62.07% of carbon, 10.34% of hydrogen, and 27.59% of oxygen by mass, and it produces an orange precipitate with 2,4-dinitrophenylhydrazine, but doesn't react with phthalings or toluenes. And the proton NMR spectrum of the compound has a single peak with a chemical shift of 2.2 parts per million. The peak area corresponds to 6 hydrogen atoms, and its mass spectrum and infrared spectrum are shown below. Use all of the given information to determine the structure of the compound. So firstly, we're going to look at the empirical formula, because that's probably the easiest thing to do first. And we can find out its empirical formula by using its composition by mass. So we do it exactly in the same way as we would normally. So we set it out as carbon, and then hydrogen, and then we also have oxygen. So carbon is 62.07%. Then hydrogen is 10.34%. And then we have 27.59% of the oxygen. So first thing we do is divide by all of the relative atomic masses. So we have 62.07 over 12.0, and this gives us 5.17. And then we have 10.34 divided by 1.0, which is equal to 10.34. Then for oxygen, we have 27.59 divided by 16.0, and this gives us 1.72. And then we divide by the smallest. So the smallest is the 1.72. So we have 5.17 divided by 1.72, and this is equal to 3.01, and then we have 10.34 divided by 1.72, which is equal to 6.01, and then finally we have 1.72 divided by 1.72, which is equal to 1.00. And so here we've divided by the smallest. And so now we have our ratio for this compound of the different elements in this compound. So we have that the ratio is equal to 3 to 6 to 1. And so our empirical formula is equal to C3H6O. And now we have to try and work out our molecular formula to actually see how many of each element we actually have in this compound, because the empirical formula is just the simplest whole number ratio. So how we do that is we look at our mass spectrum. So this one on our left is our mass spectrum. So this is what we get from our time of flight mass spectrometer. And because this is a simple molecule, we look at the highest peak, which has the highest MZ ratio. So the peak with the highest MZ ratio would be this one. However, this isn't the largest peak, and so it's not this one. So we're actually looking for this one here. And this is at an MZ value of 58. And this is what we call the molecular ion peak. And because this molecular ion peak is at an MZ value of 58, this is actually the relative molecular mass of this compound. So we have the relative molecular mass is 58. So from the mass spectrum, we have that the relative molecular mass, or the MR, is equal to 58. And so the way we work out our molecular formula is to first work out the unit of the empirical formula, and then we have to multiply everything in this empirical formula by this unit. So firstly, looking at the MR of the empirical formula, so we have 12 times 3, and then we add 6 times 1, and then we also have a 16.0. And this actually gives us 58.0. And so our empirical formula is actually our molecular formula. Because our unit of empirical formula would actually just be equal to 1. And now we can look at the other information that we have. So also in the question, it said that it produced an orange precipitate with this 2,4-dinitrophenyl hydrogen. And we know that when we react 2,4-dinitrophenyl hydrogen with an aldehyde or a ketone, so a carbonyl group, it should produce an orange precipitate. And so this tells us that we've got a carbonyl group. So we could just annotate this question. So we have a carbonyl here. And then the next bit says that it does not react with phthalings or toluenes. And so we can write this down. So we can write down that because this 2,4-dinitrophenyl hydrogen an orange precipitate when reacting with this compound, we know that it has to be either a ketone or an aldehyde, because it has to be a carbonyl compound. It has to have the C double bond O. So we've got 2,4-dinitrohydrogen forms an orange precipitate. And so this means we have to have a carbonyl. And then what we have is that it doesn't react with toluenes or phthalings. And so this tells us that we must have a ketone, because aldehydes can be oxidized further. So now we can look at our other spectrum that we have, which is this infrared spectrum. And we can see that we have a peak here, this peak, at about 1,720 centimeters to the minus 1. And looking at our data booklet, this actually corresponds to a C double bond O group. And so this validates our idea of it being a carbonyl compound. So again, we have to write that down. So we have an absorption at 1,720 centimeters to the minus 1. So this indicates to us that we have a C double bond O, so a carbonyl. So this confirms that we could have a ketone or an aldehyde, but of course we can only get a ketone because we don't have a reaction with Toluene's reagent or phthalate solution. And then finally, looking at the information we have about the proton NMR. So the question said that the proton NMR spectrum of the compound has a single peak with a chemical shift of 2.2 ppm, and also the peak area corresponds to 6 hydrogen atoms. And so because it's a single peak, we know that all of the hydrogens, all of these 6 hydrogens, are in the same environment because they only produce one peak, and they have a chemical shift of 2.2 parts per million, which, if we look at our data booklet, corresponds to hydrogen attached to a carbon, which is then attached to a carbon double bond in. So what we have from this proton NMR, we have that, and what this suggests is that we have a hydrogen attached to a carbon, and then this carbon is then attached to another carbon double bonded to an oxygen. And also we have a single peak area of 6 hydrogens. And so what this tells us is that all 6 hydrogens are in the same environment. And so the only way we can get 6 hydrogens in the same environment is if we have 2 methyl groups. So if we have CH3, and so now we can use our molecular formula and what we've learned from this proton NMR, and also that it's a ketone, to work out our structure. And because we have 2 CH3 groups from this proton NMR, that means that these 2 are then attached to the 3rd carbon. So what we have is CH3, and then because we can't attach a double bond oxygen to either of these carbons, that means that the carbon which they're both attached to has to have the double bond oxygen. And so it must be this carbon which has this double bond to an oxygen. And so our compound is actually propanone. And we can actually check this because it will form an orange precipitate with 2,4-dinitrohydrazine because it's got this carbonyl group, the C double bond O. It won't react with toluenes or phthalate because it's a ketone, so it can't be oxidized further. It does have an infrared absorption at 1,720 centimeters to -1 because of this carbonyl group. And also, we do have a hydrogen, so for example, this one here, which is attached to a carbon, which is then attached to a carbon with this double bond oxygen. So we also have this peak at 2.2 parts per million. And then finally, we do have a single peak with an area of 6 hydrogens because these 3 hydrogens are in the same environment as these 3 hydrogens. So we have 6 hydrogens in the same environment and producing a single peak because there's no hydrogens on this carbon here.